In this lesson, we're going to start to solve more difficult problems with elimination. And we're going to also write equations describing linear systems and also solve those equations. So let's first start off by remembering how we solve systems like this with elimination. So we know we could solve this with substitution by just setting these two equations equal to each other because we have a y isolated. And we've also solved by elimination where we pile one of the equations on top of each other. So if I put y equals x minus 1 on top of y equals 3x plus 5. And then if I choose to subtract it, then one of the variables will be eliminated. Note that all of my other variables and constant terms are lined up with each other, including the equal sign. So y's are lined up with y's, equal sign, x's, constant, constant. So if we're ready, let's subtract these two and watch what happens. So if I were to subtract y minus y, we're left with 0y, or just 0. Copy the equal sign, and now I have x minus 3x, and we will be left with negative 2x. And then last I have negative 1 minus 5, which would give us negative 6. So as a reminder, the reason why this worked is because one of our variables was eliminated. So now we have one equation left and one unknown, and that's x. So therefore we can solve for it. So all we have left to do is just isolate for x. So I'm going to move this negative 6 onto the other side, and I'm left with 6 equals 2x, negative 2x, divide by negative 2, divide by negative 2, and we're left with x is equal to negative 3. So that's one part of our final point of intersection. What is our y coordinate? So we're just like in substitution, we can sub it into either equation. I'm going to choose equation number 1. So sub into 1. I'm going to write equation number 1. So it's y equals, instead of x, I'm going to put negative 3 minus 1, and we have y is equal to negative 4. So we have our point of intersection, and that was a quick reminder on how we solve by elimination. So remember, substitution, we are subbing one equation into the other. When we have y isolated for, we can just set one equation equal to each other and solve. For elimination, we're going to eliminate a variable. So we're going to write our equations right on top of each other. And we can either add them or subtract them. In this case, it makes sense to subtract because when we subtract, the y will disappear. And we're left with one equation and one unknown, and therefore we can solve for x and then solve for y. Now, what if we make the equation slightly harder? How could we solve for elimination in this equation? So if it's in these two equations, if we were to try to solve by substitution, we could do that. All we have to do is isolate for a variable. None of them are really easy to isolate for. If I were to isolate for this y, I could divide everything by 2. 4 divided by 2 is a nice number. 5 divided by 2 is going to give us a fraction or a decimal. So neither are nice, but what if we try to solve by elimination? Well, if I first try to stack these on top of each other, just like this, and maybe you decide to subtract. Well, what would happen? I would have 4x minus 3x, that gives us 1x. And then I have 2 minus 4y, or 2y minus 4y, that's going to be negative 2y. And then 5 minus 7 is negative 2. Well, we're left with an equation, but we still have two unknowns. The problem with this is that we didn't eliminate a variable. So what was different between this one here and this? Well, one of the variables was exactly the same, which is why it was eliminated. Y minus y was equal to 0. Here, neither of the variables equaled each other, so we had this remainder variable that we couldn't get rid of. So now my question is, can I change one of these equations so that a variable is equal to each other? Take a look at this y value. This y value is 2, and this y value is 4. Really, what I'm trying to say is the coefficient of y is 2 and the coefficient is 4. Can I make these two look like each other? What could I multiply this guy by to make this one? Well, what if I took the entire equation and I times it by 2? As long as I multiply 2 by every single term in the equation is still equivalent. So what if I rewrote this guy as 8x plus 4y is equal to 10. Is that the same thing as this? Well, if I were to divide everything by 2, I would get this equation. So yes, it is. So what if I make this my equation? So this is my first equation. And if I make my second equation exactly what it is already, so leave it alone, and I'm going to leave it as 3x plus 4y equals 7. What if I were to subtract them now? Would it work? Well, I have 8x minus 3x, that's going to be 5x. And then I have 4y minus 4y, that's going to give us 0, which is what we want to see happen. Equals, then I've got 10 minus 7, that gives us 3. So now we have one equation, one unknown, and we can solve it. So 5x plus 0 is just 5x equals 3. We can isolate for x by dividing by 5, and we have the first coordinate of our point of intersection. It's 3 over 5. So how the heck do we find our y? Well, we're just going to plug it into any equation. I could plug it into this original one or my new one because they're equivalent, or I could plug it into 2, whatever you want. So let's just say I'm going to sub it into 2. So I'm going to write 3. Instead of x, I'm going to write 3 over 5 plus 4y equals 7. So a little bit of algebra here. I have a number times a fraction. I can always make that number into a fraction, of course, by just putting it over 1. So this is going to be 3 times 3 over 1 times 5. That's going to be 9 over 5 plus 4y is equal to 7. I'm going to bring that 9 over 5 over, so I'm left with 4y is equal to 7 minus 9 over 5. I'm going to make an equivalent denominator here by multiplying by 5. And I've got 4y is equal to 7 times 5 is 35 minus 9 all over 5. Almost done. So we have 4y is equal to 26 over 5. We're going to finish this off by just dividing by 4 on each side. So I'm going to multiply by 4 in the denominator. So that divides by 4. And I'm left with y equals 26 over 20, which simplifies to y equals 13 over 10. So if we put it all together, the x coordinate of our point of intersection is 3 over 5, and the y coordinate is 13 over 10. So some tips to remember when we're using elimination is to make sure the two equations are arranged so that the variables are in the same order and place. So we piled these on so that the x's were right on top of each other, the y were right on top of each other, the equal signs and the constant values were right on top of each other. And then remember, we're allowed to multiply equations to make an equivalent equation so that one variable term in each equation is the same. So we can multiply or divide by any number in the first equation and or the second equation to make that happen. Then we can choose whether we want to add or subtract the two equations. So we've been deciding to subtract the two equations, but sometimes it makes sense to add, and we're going to look at some examples with that. Let's try some examples by solving by elimination. So if we weren't asked to solve by any method we could just choose, it looks like substitution would be nice and easy because we could isolate for that y quite easily by maybe moving it to this side and moving the 0.5 onto the other side. But let's practice elimination. So we want to pile these on top of each other and then either add or subtract in order to eliminate a variable. If I were to pile these on top of each other, if I add them or subtract them, a variable won't be eliminated because we don't have a variable term that matches. We have 2x here and 3x. That's not going to match. So it's not going to be eliminated if we add or subtract. Same with the negative 3y and the y. But what could I multiply either of these two by to make a variable match? Well, the x's are a little more difficult. The lowest number or coefficient that I could make these match with are 6. So if I multiply this by 3, I would get 6x, and this x by 2, I would also get 6x. But that seems like a lot of work. Take a look at the y's though. This term, variable term, is negative 3y. This variable term is negative 1y. What if we were to take this and just entire thing and multiply it by 3? Wouldn't it make the y's match? My new x variable would be 9x. My new y variable would be negative 3y. And then my constant is 1.5, which is what 0.5 times 3 is. So now, if I make this my new equation, let's actually call this equation 2, and this my equation 1, are we going to have variables that match? Well, negative 3y, they will. So let's pile them on top of each other. Notice how the x's are on top of each other, the y's are on top of each other, the constant and the equal signs are right on top of each other. So I'm going to put a big line underneath, and it makes sense in this case to subtract them because these two match. So let's go ahead. We know we've done it right if one of the variables gets eliminated. So we have 2x minus 9x. That's going to give us negative 7x. Then next I've got negative 3 minus negative 3. That's like negative 3 plus 3, and that's going to give us the 0 that we're looking for. So it's going to give us plus 0y, or just 0. And then we have equals negative 2 minus 1.5. It's going to be minus 3.5. We can now have one equation, one unknown, so we can solve. So I've got negative 7x is equal to negative 3.5, and let's divide by negative 7. And we get positive 0.5. So we have the x coordinate of our point of intersection. Now let's find our y coordinate. So we can find our y coordinate by plugging it into x into any of these equations. Same as substitution, all those questions that we did. So I can plug it into this guy. I can plug it into my equation 2 version 1 or my equation 2 version 2. It does not matter. This time let's just plug into equation 1. Okay, so my equation 1 is 2. Instead of x, I'm going to put in 0.5. Minus 3y is equal to negative 2. So I have 2 times 0.5, just 1. Minus 3y is equal to negative 2. Bring that 1 onto the other side. And I've got negative 2 minus 1. And then I have 3y is equal to negative 3. Divide by negative 3, divide by negative 3, and I'm left with y is equal to 1. Therefore, our POI of this system is the point 0.51. Let's look at another example. So, substitution, if we were to do it, not so easy here. It's not so easy to isolate for this x, this y, this x, this y. So this might be a good time to use elimination. I know we're supposed to use elimination, but this is sort of the reasoning that you can start to go through in your mind when you're coming up to questions like this. So the question is, what's going to be the easiest variable to make match? So I see a 9x and a 3x. I know I could multiply this equation by 3 and it would give me 9x, and then I could cancel them out. That could totally work because 3 times 3 would be 9. Also, look at the y's. I have negative 4y here and positive 2y here. I could multiply this guy by negative 2 and make negative 4. Another thing I want to show you is, what if we multiplied this equation by 2 instead of negative 2? What would happen? By the way, all the other options that I said would totally work. I just want to show you something different. So we could have multiplied this guy by 3 so that the 9x and the 3x worked. We could have multiplied this guy by negative 2 so that this would make negative 4 and that would match that guy. Let's just try multiplying by positive 2, and there's a method to the madness. So let's just see what happens. So my new equation 2 would be 3 times 2 is 6x plus 2y times 2 is plus 4y, and that's going to equal 20. So I don't have a variable that matches, but I have one that's opposite. And I mentioned that sometimes we can choose to subtract the equations like we talked about, but we could also choose to add them. So let's pile them on top of each other. So now that we have them piled up on top of each other, if I were to subtract these don't match, it's not going to work. I did negative 4 minus 4, that'd make negative 8. But what if I were to put a big plus sign here and we add the equations together? Is that going to eliminate a variable? Well, this guy, 9x plus 6x, that's definitely not going to eliminate. 9x plus 6x is going to be 15x. But take a look at this guy. Negative 4 plus 4. Negative 4 plus 4 is just going to be 0. So we have eliminated a variable, this time through addition. And then I have 10 plus 20 is going to make 30. And now I've got one equation and one unknown, so I can solve it. So with elimination, we can eliminate a variable by subtracting. Also, if it's easier, if we have opposite variables, we can just eliminate them by adding. That's allowed too. So let's just solve for this guy right here. So we've got 15x is equal to 30. Divide by 15, divide by 15. And I have x is equal to 2. So we have the first part of our coordinate of our point of intersection. Remember, you can plug it into any one of these equations to find the y-coordinate. So once you try that on your own and come back to the video once you've got it. So if I chose to plug it into equation 1, but you could have plugged it into any equation, 1, 2, or our equivalent of 2. And you should get the solution of y is equal to 2. Therefore, our point of intersection is the point 2, 2. We've come to our last example. So if we were given a choice of how to solve this, really no method is going to be really nice. Because if we try to solve this by substitution, getting x or y here by itself is not going to be pretty because we're going to be dealing with a number over 3 or over 7. We're going to be dealing with fractions. Same with this here. No number is going to no variable can be really easily isolated for. Now we think at elimination and we start analyzing these variables. How the heck can we make these variables equal to each other? Well, 3 doesn't we can't make into 5, and 5 we can't make into 3. Neither 7 into 8 or 8 into 7. So what we're going to have to do is we're going to have to multiply not just one of the equations by a number, but both of the equations by a number. So taking a look at 3x and 5x, I know I could make 15x. I could make this one into 15x by multiplying it by 5, and this one into 15x by multiplying it by 3. So now we're going to multiply both equations if we get really, really stuck. So I'm going to multiply this equation by 5. I'm going to multiply this equation by 3. So we have two new equations. So my new equation 1 would be 15x minus 35. Y is equal to 11 times 5, which is 55. And then my second equation would be 5x times 3, everything times 3. So 15x plus 24y is equal to 27. So now we can see we can use elimination on this because I have two variables that match. So I'm going to pile 1 under 2, or 1 on top of 2, and I'm going to subtract them and solve. So try this entire question on your own now that we've got our two variables that match, and come back to the video once it's completely solved. Alright, so if you're coming back to the video, that means you've done this one on your own, you tried it. So there's some good fraction work. Do not change into approximated decimals when we can keep everything a perfect solution with fractions. So the first thing we did was pile those equations onto each other. If you put equation 2 over top of equation 1, you're still going to get the same answer of this guy right here. So once we subtract them, we should have this as our final answer for y. And then we can sub that y into any of the 4 equations because we have our 2 original and then we have our 2 new ones. I decided to sub it into this ugly fraction into one of the original equations. And the reason I did that is because the numbers were smaller and I just didn't want to deal with even larger numbers than what I already have. So I chose to start with smaller numbers, this guy right over here. So I put our y into this equation and solved and solved and solved and solved, and here is our x. So if you got something different, there's probably a small arithmetic error, calculation error. Just go through your work very, very carefully, figure out where it is. Now let's try to solve a problem that doesn't give us equations, but give us the problem in words where we have to come up with the equation and solve it. So this question says each gram of a mandarin orange has 0.2 milligrams of vitamin C and 0.3 milligrams of vitamin A. Each gram of a tomato has 0.13 milligrams of vitamin C and 0.42 milligrams of vitamin A. I'm just going to try to highlight these to keep these numbers sort of in order in my brain. So an orange has this much vitamin C and this much vitamin A, and the other guy, a tomato, has 0.3 milligrams of vitamin C and 0.42 milligrams of vitamin A. So the question says, how many grams of mandarin oranges and tomatoes would someone have to eat to consume 13 milligrams of vitamin C and 20.7 milligrams of vitamin A? So what are the things we don't know? Well, it's asking how many grams of mandarin oranges and tomatoes would someone have to eat. So the two things we don't know is the number of grams of mandarin oranges and the number of grams of tomatoes that we're going to eat. So the first thing we can do is define our variables. So let's let M represent the total grams of mandarins and T represent the total grams of tomatoes. So now let's use this information that we're given. We've got all this information about mandarins and tomatoes, and what's the goal? We want to consume 13 grams of vitamin C, a total of 13 grams of vitamin C, and 20.7, milligrams of vitamin A. So what do we know about vitamin C? Well, the total vitamin C that we want is 13 milligrams. And we know that has to be equal to the milligrams from a orange or a mandarin plus the milligrams from the tomatoes. By the way, if you think this is a silly question, they're all kind of silly questions, but let's just keep going with it. Okay, so what the heck are the milligrams for mandarins? Well, taking a look back to our little highlighted yellow, we get 0.25 milligrams of vitamin C from 1 gram of a mandarin. So that means that our milligrams from a mandarin of vitamin C are going to be 0.25 times M, because M is the total grams of mandarin. So if there's 1 gram of a mandarin, we get 0.25 milligrams of vitamin C. If there's 2 grams of a mandarin, we're going to get 0.25 times 2. And how about milligrams from a tomato? Well, we get 0.13 milligrams of vitamin C from a tomato. So that's going to be 0.13 times the total grams of a tomato. And that must equal 13. So this must be our first equation. Now let's talk about vitamin A. The goal is to get a total of 20.7 milligrams of vitamin A. And that has to be made up of the milligrams that we get from mandarins plus the milligrams we get from tomatoes. So the milligrams of vitamin A we get from mandarins are 0.13 milligrams for every gram of mandarin. So we can say that that's just 0.13 times M, because M is the number of grams of mandarin, plus from a tomato we get 0.42 milligrams of vitamin A from 1 gram of tomato. So that's going to be 0.42 times the grams of tomatoes. And this all has to equal a total of 20.7 milligrams of vitamin A. So now we have our second equation. So now the question is, what are the values of M and T so that both of these equations are true? Well, if we were to try to use substitution, this is an ugly example to use substitution for, because I don't want to isolate for M or T in either of these equations, because I don't want to divide by this decimal. So let's try elimination. First of all, What's nice is that the equations are sort of lined up, one on top of the other, where all our variables match up, our equal signs match up, our constant terms match up. The problem is we don't have a variable that matches. Is there an easy way to turn, let's say, 0.13 into 0.42? Well, if you divide 0.42 by 0.13, it's not a pretty number. It's a decimal that goes on and on and on and on. So it's not going to be nice to turn this guy into this guy, for example, or same with the m. But what we could do is we could multiply both equations by a number. So this is like the ugliest example we can find. So if we can do this example, we can do any example. So let's try to make, why don't we say let's make the m's the same? Well, these are two very ugly numbers, but if I multiply this one by 0.25 and this one by 0.13, then the m's will have the same value. So one more time, if I were to take this equation and multiply it by 0.13, which is the value of this m value, if I were to multiply this guy and multiply it by 0.25, then my m values will now be the same. So let's redo our two equations. Our first equation, everything's going to get multiplied by 0.13. So my first number is 13 times 0.13 is going to give us 1.69 equals 0.25 times 0.13 is going to give us 0.0325. Don't get rid of any decimals because then we're going to have an inaccurate number. Plus, now I'm going to do this 0.13 times 0.13 and we get 0.0169 t. There's our first equation. Let's put our second equation right underneath. So our second equation, everything's going to get multiplied by 0.025. So I'm going to multiply 20.7 times 0.025, and I get 5.175 equals, then 0.13 times 0.25, and that's going to give us 0.0325, which is exactly what we wanted because we wanted those m's to match, and now they do. And then I'm going to put 0.42 times 0.25, and that gives us 0.105 t. And now we're ready to do elimination because we have a variable that matches. So let's subtract these. So first I got 1.69 minus this guy, minus 5.175, and we get negative, we get negative 3.485. Don't get rid of any decimals because then we're not going to be accurate anymore. We're going to subtract these two and we'll get 0 plus, then we're going to subtract these two and we get minus 0.0881t. Let's quickly isolate. So we've got negative 3.485 is equal to negative 0.0881t. Let's get that t by itself by dividing by this ugly decimal. Dividing 0.881. These are going to cancel out. We're going to left with t is equal to. And now we're left with a very long decimal. So why don't we take 3 to 4 decimal places for now. So it's 39.557 approximately. So that means that we need to consume approximately 39.557 grams of tomatoes to make our little diet work. Now let's figure out oranges, and we can, mandarins, and we can figure out the amount of mandarins. Think of this as like our x value. Let's come up with our y value now, which is m, or vice versa. It doesn't matter which one's x, which one's y in this case. So we can find m by plugging this guy into either of these equations. Not only these equations, we could have plugged into this original equation or the one above it right up here. We could have also plugged it into this guy right here. So if I'm really trying to be wise with my time, I'm probably going to choose an equation with nicer numbers. These aren't beautiful, but these are a little bit nicer. So I think I'm going to plug mine, 39.557, into equation number 1. So I took the equation 1 that we have above in red, and I wrote everything out except I replaced t with the t value we already have. And now we're just going to solve. So I'm going to simplify 0.25 m, and then I'm going to throw into the calculator 0.13 times this guy, and we get, and we get 5.14241. Bring this onto the other side. 14241 equals 0.25 m. If I subtract the 2 on this side, I got 7.85759 equals to 0.25 m. Let's finish this off by dividing by 0.25 and dividing by 0.25. So I'm left with m is equal to approximately 31.430. So in conclusion, we need to, for this special diet where we're supposed to get 20.7 of one vitamin, and I can't even remember how much of the first one, 13 of the second vitamin, we need to eat this many grams of mandarins, 31.430, and this many grams of tomato,